Towards the end of the yesterday's class, we have been talking about solutions of the Ising model. Essentially, we are talking about one dimension, and we have shown that there is a technique called as a transfer matrix approach, which allows you to calculate the partition function in a closed form, and this amounts to actually solving a 2 by 2 matrix, or rather it is a multiplication of n 2 by 2 matrices which are all identical, and then one can calculate the partition function as trace of the sum of the eigenvalues. This is known that this is how the solutions of a 2 by 2 matrix comes about. So, all it boils down to is calculating the eigenvalues, and hence the eigenvectors which we have not used, but we will use that now, and get some properties of this 1D Ising model. So, we will do a little bit of follow up on the transfer matrix approach, and then we will talk about mean field theory. And again the third technique that we will be talking about is the renormalization group, which is also known as the poor man's RG, or it is also called as the Kadanoff technique or Kadanoff transformation, and these will wrap up the solutions of the 1D Ising model, which shows a distinct transition from the paramagnet to a ferromagnetic phase. And this is possible in any dimension which is greater than 2, and exact solutions, as I said, are available in only 1 and 2 dimensions, and we are simplifying the discussion by following in or rather resorting to only 1 dimension. And but of course, when we do the mean field theory, you see that it is kind of irrespective of dimension, and then we will do the renormalization group. So, just a little follow up on the transfer matrix that we did. So, we wrote down the partition function, which is equal to lambda 1 to the power n and lambda 2 to the power n, and where lambda 1, 2 are 1 and 2, these are the 2 eigenvalues which are written as exponential beta j, cosine hyperbolic beta j, plus minus we have this exponential 2 beta j, and plus sine hyperbolic square beta h plus exponential minus 2 beta j. Okay. And this is derived yesterday. These are the 2 eigenvalues, where j is the nearest neighbor interaction between the spins, and h is the effective magnetic field, or just the magnetic field. There is a factor of this magnetic moment that is included there, but let us not worry about that. So, these are the 2 eigenvalues, and my z is, or the partition function is obtained in a closed form using the lambda 1 and lambda 2. And as I said that because of this plus and minus signs, and then you have these each of the eigenvalues is raised to the power n, one can neglect these lambda 2 in front of lambda 1. Lambda 2 corresponds to the negative eigenvalue, and lambda 1 corresponds to the positive eigenvalue. So, lambda 1 is greater than lambda 2. So, lambda 1 to the power n is much greater than lambda 2 to the power n, and hence can be neglected. And you can actually write this down as lambda 1 to the power n, or even if that is not appealing to you, which should in the limit n going to infinity, you can keep both lambda 1 and lambda 2 to the power n, and write down the free energy, which is equal to minus kT log of lambda 1 to the power n plus lambda 2 to the power n, and this can be written as minus kT n ln lambda 1 plus ln 1 plus lambda 2 by lambda 1. I have kept both these things. Let us put a second bracket here and hold to the power n, and so this is the expression for the free energy, and you can now neglect this because it is to the power n, and then it's inside a log. So, we can simply write this as minus nkt lambda 1. Okay. And we have worked out that the magnetization is nothing but this derivative of the free energy with respect to the field, and if you do it carefully, it comes out as sine hyperbolic beta h divided by root over of sine hyperbolic square beta h plus exponential minus 4 beta j, and it is very clear that for h equal to 0, m equal to 0. So, no spontaneous magnetization, which is what we have learned. And this result, as you will see, that is in direct contrast with mean field theory, and so the mean field theory is infinitely wrong in one dimension. It becomes increasingly correct as you go to larger and larger dimensions. Okay. So, and of course, you can see that for h not equal to 0 and beta to be large, which means small temperature, we have all of them to be pointing along the same direction. So, m actually tends to 1. Okay. So, these are the two limits that are of importance to us, and these limits have been in some form have been obtained in the earlier as well when we have dealt with non-interacting spins, and now they sort of seem to give you similar results. That is, this 1D model has no spontaneous magnetization. So, that is like saying that the energy difference between the disordered state or a paramagnetic state and the ordered state, which is ferromagnetic state, is infinitesimally small. So, at no finite temperature, the model shows any magnetic property or ferromagnetic property. Okay. Which means that it is only at t equal to 0, and t equal to 0 is really an ideal situation when we are not talking about exactly at t equal to 0. And we will see, as I said, that this result, it contrasts with the results obtained from the mean field theory. But before that, let us use to find this transfer matrix to find the correlation function. So, correlation function via the transfer matrix, or correlation length, you can say that, which is a more physical phenomena via the transfer matrix. So, what we mean is that suppose you have an upspin at a site say I, and you have another upspin at a site which is say at a distance r apart. R can be anything, and r in principle goes to infinity for an infinite system. So, you ask this question, that what is the probability that if I have a spin up at a given site, which is my reference site, and then at a distance capital R apart, what is the probability that I get another spin which is also pointing up, and this is called as a spin-spin correlation function. If in the limit r going to infinity, I still have this probability to be large, then this says that the system is ferromagnetically ordered, and hence it represents a ferromagnetic phase of the model or of the system, a ferromagnetic state of the system, and that is what we want to calculate that. So, what is the spin-spin correlation function, or we can cast it in a different form, that was the correlation length. So, what is the length over which two spins are correlated, that is both are pointing up or both are pointing down. Okay. I mean, in this case we are just assuming that the magnetic field is in the upward direction, which will eventually at the ferromagnetic state, all spins will be pointing in the direction of h, okay, and h is upward. So, we are talking about the upward direction to be the favored direction. So, this correlation function, let us write it as some two sides of the system on the chain. It is a one dimensional chain, and implicitly here we have assumed a periodic boundary condition such that the last spin and the first spin, they are connected and they interact, these spins interact via this interaction term J. So, we need to calculate quantity such as this. Let me write it neatly. So, it is SI minus the average of SI and Sj minus the average of Sj, and you take the expectation or the average value of that. So, the this angular bracket that you see is actually the thermal average. Okay. So, which means that it has to be multiplied by exponential minus beta h and finally take the trace and things like that. Okay. So, what we can assume is that if you have a translational invariance of the system, then each of these expectation values, which are simple numbers, should be equal to S, and which we later call as a magnetization of the system. So, independent of the site indices I and j, they have the same value, which is expectation of S. Okay. And in this limit, the gamma Ri Rj, which is the correlation function, I should define it. So, Ri Rj is equal to gamma of Ri minus Rj. Okay. So, they do not depend upon, or rather the correlation function does not depend upon individual site indices, but its difference between the two sites, and this is often done in physics in various branches, where whenever you have a translational invariance or there is a periodicity in real space, then we do not need to talk about these two indices separately, these two lattice indices or site indices separately, but we can talk about the difference between the two. So, it becomes from two variables, it becomes just a one variable, which is Ri minus Rj, difference between the two sites. And this is then equal to, if I open up the bracket, it becomes equal to Si Sj and minus S square, okay, which is this Si or Sj that. So, if you look at the middle expression, then it is equal to the second term, which is S square. So, the implicit assumption is that the spin correlation or the spin-spin correlation, again let me reiterate, it means that was the probability that you have an upspin at a site I, and also there is an upspin at a site j, where I and j are arbitrarily far apart. And this tells you that if this probability is large, then we have a magnetic ordering in the system, which means that every spin is pointing in the upward direction, which corresponds to a ferromagnetic state of the system, and that is what we are trying to find out. So, this spin correlation function, we just call it a spin correlation, or you can call it a spin-spin correlation. This actually dies exponentially rather. So, it dies away as r tending to infinity, in the sense that if these the two spins are very far apart, the usual behavior is that it goes to 0. So, that we can write this thing as the gamma Ri minus Rj as some exponential minus Ri minus Rj divided by xi, or it can be written as exponential minus r over xi, where r is equal to Ri minus Rj. That is the mod of this. Okay. So, now this spin correlation dies as r goes to infinity, means that as you increase the distance from one site to another, the probability that you would get again another upspin at an infinite distance really dies out. And this is not only true for below Tc, that is below the transition temperature where the magnetic correlations occur, it is also true at T greater than Tc. The only difference is that that you have above Tc, you have this equal to 0. This quantity is equal to 0, which is called as a magnetization, and below Tc this quantity is not equal to 0, it is finite. But nevertheless, this behavior stays as you go from as you make the distance between the two sites under consideration to be large enough. Okay. So, let me take one site as labeled as 1 and another site which is at a distance apart as r. Okay. So, we are trying to find out the correlation between S1 SR kind of thing. Okay. So, this kind of and will of course, the limiting case for this for us to consider is capital R tending to infinity. So, what is then gamma of R, which is the distance between the two spins, where 1 is the origin of the coordinate system, say. So, it is S1 SR and minus S1 SR, okay. And that goes as exponential minus R over xi, and we are interested in calculating xi. Okay. So, that is the whole idea, and so it is easy to see that if I take the log of this, this is equal to minus R over xi. That gives you that 1 over xi, which is called as the correlation length. We will write that. So, this is the correlation length. Simply stated is the distance over which the spins are correlated. So, this is equal to minus 1 over r log of this thing, and we know that this is equal to the gamma r is given in the top line. Okay. So, this is minus 1 over r log of S1 SR minus S1 SR, and if you want you can take a mod of that, but it does not matter. So, this is what we have to calculate. Okay. And suppose we are above TC. And then each of those S1 equal to SR, that is equal to 0, because the average value of the spin there is 0. We are only taking that the second term vanishes, and in which case your log of gamma r is minus 1 over r log of S1 SR, just making things a little simple. And at the end we will see that it really does not matter if you keep or rather keep these terms. So, that is a constant term, it is something like an m square kind of term, where m denotes a magnetization. At this moment we are just interested in calculating this thermal average S1 SR, where 1 and R are two different sites. All right. So, what is then S1 SR correlation? This is equal to the sum over spins S, and then we have S1 SR. This is how any thermal averages are calculated. Throughout the course we have seen that, and you have a En, and then there is this S, and this S in the curly bracket simply means that the all possible orientations of S, which in this case is just plus and minus 1. Okay. And then you have to divide it by the exponential minus beta En, which is the partition function of the system. Okay. This is simply 1 over z, and this S, this curly bracket, let us keep it, and it just means that all the S's they can take values plus and minus 1. So, e to the power minus beta En, and you have S. Okay. So, this is the quantity that we have to calculate, and we will use the transfer matrix that we have learned. And if you see that, it is actually very simple in terms of the transfer matrices. It is S1 and then all the transfer matrices, because this has those values which are exponential. So, En has this form which we have said it is equal to some minus beta, I mean not beta, beta is here. So, it is equal to that H sum over I Si and minus j and Si plus 1. Okay. And so, these things can be written in terms of these transfer matrices, which are like T23 and all the way Tr minus 1 Tr. We go all the way up to this rth spin, and then we write a Sr, and then we get a Tr and all the way up to Tn. Okay. So, these are the transfer matrices that we have seen, I mean here, and here as well. Okay. So, these are the transfer matrices that we have calculated. All right. So, then we can easily sort of simplify this, because these are multiplication of 2 by 2 matrices, and they simply become equal to S1, and there are R of them. So, it is T to the power R and the 1 R component, and then there is a SR, and then again this N minus R of the transfer matrices, and this is the R1 component. Okay. And so, this then becomes equal to gamma of R becomes equal to, using this is equal to minus 1 over R. See the expression that we have written in the last slide. So, this is a log is there, log, and then we have I, which is not equal to 1, not equal to R, excepting these two. We have lambda I by lambda 1 to the power R, and we are now taking this U1, S1 and UI, UI SR U1. Okay. U's are the eigenvectors of the transfer matrix. Okay. And lambdas are of course the eigenvalues of the transfer matrix. You see there is a sum over I. Now, I cannot be equal to either 1 or R. Now, this T to the power R, the 1 rth element is nothing but this, and this element is nothing but this, and then we have to sandwich these, this means that this is actually equal to this and this is equal to this. Okay. The second this expectation value. So, we are taking expectation value of the S1 spin. Of course, S1 can take values plus and minus 1 between the eigenvectors, the first eigenvector of these transfer matrix, and squeezed between the ith eigenvector. I is a running index, and then this is the rth spin, which again can take values plus and minus 1, and squeezed between the UI and the U1. Okay. So, that is the R1 value. Okay. So, we just need to now calculate the lambdas and the u's, but you see there is this one will only peak when I equal to 2. So, that is the neighboring site where the correlations will be maximum. So, R really would this value would have a maximum value, or rather this gamma R has a maximum value when your I is equal to 2, which is the nearest neighbor of 1. Okay. And so, if you calculate U1 and U2, let me also write down that this is maximum when UI equal to U2. Okay. And this is an important thing. So, let me do box of this. All right. So, now we can calculate u1 and u2, and when we do that, we also need lambda 1 and lambda 2, and then the gamma r, which is the correlation function, that comes out as lambda 2 by lambda 1 whole to the power r e to the power minus 2 beta j, and divided by e to the power 2 beta j sine hyperbolic square beta h, and plus exponential minus 2 beta j. Okay. So, this is the correlation function that we get, and this correlation function now can be analyzed, and then if you put H equal to 0, that is the magnetic field equal to 0, then this is nothing but, so this term goes away, and we have a term which looks like a tan hyperbolic term, and this then in that limit this looks like so this is for beta equal to 0. So, that is like infinite temperature where the correlation is not decaying at all, it is constant at infinite temperature, and it if you at any finite temperature. So, finite beta. Okay. So, this is gamma r plotted as a function of r. So, as you increase r, the correlations fall down, and then one can calculate. If you any finite beta, you will have a fall off from this, and then of course, at beta equal to 0, it is a constant line, okay, which does not fall off, and the correlation length now can be written as so xi is equal to, or 1 over xi, inverse of that is minus log of exponential beta j cosine hyperbolic beta h, of course, at h not equal to 0, and square root of exponential 2 beta j sine hyperbolic square beta h, and plus exponential minus 2 beta j, and then divided by exponential beta j. I mean, this log will have both. So, exponential beta j cos hyperbolic beta h, and a plus, and this exponential 2 beta j sine hyperbolic square beta h plus exponential minus 2 beta j. Okay. So, this is the correlation length, and this correlation length is an important quantity in the discussion of phase transition. So, if you have at t equal to 0, if you are at t equal to 0, then xi inverse goes to 0, which means xi goes to infinity, which means that there is a phase transition. Okay. So, this means there is a phase transition, and then at t going to infinity, those are the two familiar limits for us. So, your xi inverse going to infinity, which means that xi goes to 0, we have a paramagnetic phase. So, you can study the phase transition by looking at the behavior of psi. This is often done in many phase transitions. So, this concludes the topic of this transfer matrix, and let us now go on to another topic, which is called as a mean field theory. And what is a mean field? The word mean means, of course, average, that you know, and it sort of tells you that we have many spins in the system, and what we do is that we consider the effect of all other spins on a given spin as an average field. Okay. Think of people sitting in the class, and one could be sitting very far away and one could be sitting very close to a particular student, and the effective field on the students, or the average field or the mean field on the student, we replace the effect of all other students by a single effective kind of field, as if the student is influenced by someone who's sitting very far away and someone sitting very close by equally. So, this is called as an average field. So, what we are trying to get at is that if you have a large number of spins, and if you only concentrate or focus on only one spin, the presence of all other spins in that system only poses an average field on this, and this you can understand that this is somewhat of an approximation, because something which is very far away and something which is very close by of that particular spin which is under consideration, they should have different effects. But this mean field theory neglects that, and this is called as the fluctuations or the thermal fluctuations. So, the thermal fluctuations are neglected in mean field theory, and because of this neglect of fluctuations, it often gives you wrong results. But in some cases, particularly in higher dimensions like 2 dimensions and 3 dimensions, it gives you qualitatively correct results, even though it is quantitatively wrong. Unfortunately, in 1D it gives a wrong result. It will give you a result a priori that it has a spontaneous, or 1D Ising model has a spontaneous magnetization in 1D. And in fact, as we do this analysis, you will never see actually the dimensions coming by excepting through what is called as a coordination number, and the coordination number indicates that how many neighbors that a spin has. So, in 1D one particular spin has 2 neighbors, and in 2D it has 4, and in 3D it is 6, and so on and so forth. So, the only information of the dimensionality of the problem enters through the Z or the coordination number, and so it is equally applicable in all dimensions. So, and as I said, in 2 and 3 dimensions it gives you qualitatively correct results, maybe quantitatively wrong. Wrong means it is inaccurate, and the results that we are talking about is really a transition temperature at which a ferromagnet to a paramagnet transition that occurs. So, it is a TC that we are most interested in. Okay. So, we know the strength of mean field theory now, that it qualitatively can reduce a very complicated spin interacting problem, not only in spins, but in other areas as well. But however, the limitations that when the fluctuations dominate, then it starts giving wrong results, and in lower dimensionality the fluctuations are very large, and that is why it gives you wrong results. So, what we do is that we try to sort of take an arbitrary spin at say some SI, and try to do concentrate on that and replace all other spins in the vicinity, either 1, 2 or 3D, to be as an effective field. Okay. So, we write down SI equal to some average value plus some fluctuations. Okay. And in the quadratic case, the fluctuations will be ignored. Let us see that. So, we have this delta SI, which is this fluctuation is equal to some SI into SI average. Okay. That is the fluctuation in spin. So, we have a term which is like SI SJ. We are not writing SI and SI plus 1, because we have committed that this analysis is correct in any dimension. So, we will write I and j instead of I and I plus 1, and this is equal to SI plus a delta SI and Sj plus a delta Sj, and we open up the bracket and Si Sj, and then we have a Sj and a delta Si plus a Si delta Sj, and then finally a term which is a plus delta Si delta Sj, and this being the fluctuation, and in quadratic in fluctuation, this can be said to be 0. Okay. So, these are two small quantities being multiplied and that is equal to 0. So, that is really the approximation that we count, and in some cases of course, this term cannot be neglected. Anyway, we are leaving that, and we have now these 3 terms that we have, and we can again do a little bit of replace delta Si by these by this expression that you see here. So, you put it here and you put it here, and then what one can get is this Sj Si and plus Si Sj and minus Si Sj average of both. Okay. So, what we do is that we sort of reduce an interacting problem, that is 2 spins interacting, to a sort of non-interacting problem where each spin is facing a field due to the other. So, this is just a number, it is called a C number, and this is just a number as well. Okay. So, these two are numbers, and you now have one spin, and then becomes a non-interacting problem, it becomes a one particle problem, which can be solved exactly. Okay. So, within this approximation, we sort of reduce the Hamiltonian, and what we do is that we further assume that Si equal to Sj equal to m. And we have seen this earlier, that when you have translational invariance, you can write it down as them to be equal, that is Si average and Sj average are equal, and that is equal to m. Just to remind you that these are we are talking about the thermal averages. Okay. So, what does Si Sj, it boils down to m Si plus Sj and a minus m square, and then you can take a m common and you can write it as a Si plus Sj minus m. Let us put a bracket here, and this is the Hamiltonian, the one particle Hamiltonian or the mean field Hamiltonian that we get. Okay. And let us write down this Hamiltonian and see that how that can be solved. So, we write down now the mean field Hamiltonian, MF stands for mean field, and this is equal to minus Jm. We have a Si plus Sj minus m, and a minus H Si I equal to 1 to n, and of course, here I j are nearest neighbors. Okay. And both of them actually go from 1 to n. And needless to say that Si sum over I equal to Sj sum over j. In a translationally invariant system, the space does not matter, in the sense that whether you are talking about I site or j site, they would yield the same result. Okay. So, that tells you that so sum over Si plus Sj can be actually replaced by just one index, which is sum over twice sum over Si. Okay. They being same. All right. So, now the Hamiltonian becomes even simpler, or at least the look of it is simple, and which can be written as minus Jm, and then there is a I, well, I mean there is no j, so we can simply write it as I, and then we have a 2 Si minus m and minus H Si and so on. Okay. So, I. Now, what we will do is that we will replace this sign or rather the sum over I as it is half sum over actually this sum over, when you have a I and j, ij being the nearest neighbor, and when you write it as 2 over Si, we can bring in a factor of 2 here, because I and j should not be counted twice. So, each pair should only be counted once, and that is why in this term we take a factor of 2 there. So, this can just be simply this it just becomes, there is a factor of half, and the mean field Hamiltonian really takes a simple form. There is also another thing that comes here, is that because you have a j, so there is a sum over j along with the I, j being the nearest neighbor, and this sum over j really gives the z, which is the coordination number, which is a number of nearest neighbor spins which need to be taken into account. So, we have a z that appears here. So, once when you go from a double sum involving nearest neighbors, so corresponding to each I there are j's, and in one dimension there are two j's on either sides, plus x direction and minus x direction. In 2D we have a plus y minus y, and 3D we have plus x plus minus y and plus minus z. We have this z as a coordination number, and this is exactly what I was saying, that the dimensionality information only enters through this z and nothing else, because it's just a one particle Hamiltonian in any dimension. So, there is no really dimensionality that we need to worry about. Okay. So, we have this problem now that we have this Hamiltonian, and this Hamiltonian can be a little, can be farther simplified, and we can write it as nz m square with a j term. Let me sort of follow certain order of writing this. M square by 2, there is a m there inside and there is a m outside there, and there is a h plus z j m, and then there is a sum over I and S I, okay, and I of course goes from 1 to n. So, this is the Hamiltonian, mean field Hamiltonian that we need to solve, and this will give us results that we have to analyze. Okay. So, let me just write z equal to 2 in 1D, equal to 4 in 2D, equal to 6 in 3D. Okay. So, this can be written as some H effective, okay, where H effective is nothing but H plus ZJM. All right. So, we can solve this Hamiltonian, and we can calculate the partition function now. And the partition function yields ZMF is nothing but a trace of exponential minus beta HMF. Okay. And this we know, and this is not difficult to calculate, because we know that so this is really like a product of I equal to all the sides basically, or all the spins that are there, and then we have this SI which takes values plus and minus 1, and then exponential minus beta H, sorry, it is not FM, it is MF. And this is what we have to calculate. Unfortunately, there is a closed form for this. It is really easy to do that. So, ZMF is simply equal to exponential minus beta NZJ m square by 2, and then the product of I equal to 1 to n, and then we have a sum over SI equal to plus 1 and minus 1 exponential beta H effective SI. Okay. So, you have one part that factors out which contains this j term, z is the coordination number, beta equal to 1 over kt, j is the nearest neighbor spin-spin interaction, m is expectation value of SI or SJ or of that or any S. This actually gives you a 2 cosine hyperbolic beta H effective. That is easy to see, you just put a plus 1 and minus 1 here, it will have a 2 cosine hyperbolic term. So, the ZMF actually gives you a form which is exponential minus beta NZJ m square by 2, and we have n of them because each one is 2 cosine hyperbolic H effective, beta H effective. So, please write it neatly so that you are not confused. This is a cos hyperbolic term, So, this H and the H that you see afterwards are not the same thing. I mean, in any case here it is H effective, and this is the closed form of the partition function. So, this tells you that you are very likely to arrive at a solution which is in closed form, and we can now of course calculate the magnetization, and from the free energy, that is, you take the log of this partition function, multiply it by minus kT, and then take a del f del h. But what we can do also here is that we we know this, that m is equal to 1 over n, I equal to 1 to n SI average, and we can calculate the SI average using the formula that it is a SI trace of exponential minus beta h divided by z, and this is easy to see that it is equal to sum over 1 to n a trace of SI exponential minus beta HMF and divided by the ZMF. That is what we have calculated, and this is again equal to 1 over n ZMF, and we have a sum I equal to 1 to n SI into e to the power minus beta HMF, and so this can be written as 1 by n beta 1 by ZMF del ZMF divided by del H effective, and we just show you that how we can write this, that is coming from here to here. Just show it in a moment, and this is equal to 1 over n beta del ln ZMF and del H effective. So, let me show this step that comes. So, we have a del Z MF by del H effective, and that is equal to del H effective divide into trace of exponential minus beta H MF, the mean field, and this is equal to trace of we can take it inside because the H effective is only there in exponential minus beta in the HMF. So, this is trace of del H effective, and we have exponential minus beta HMF, and this is nothing but minus beta trace of del H effective of HMF and exponential minus beta HMF. Okay. And this is equal to beta because you are taking this del H effective of HMF. So, this is equal to beta, and you have a trace of sum over SI and exponential minus beta HMF. Okay, and that is what we have said here. So, when we came from the step on the last but one line to the first expression on the left, we have used this. So, this is fine, and then now we go and calculate log of Z MF, which is equal to from the expression that we have for ZMF, we can use that, and we get this beta n Z and j m square by 2, and then we have n log 2 plus n log of 2 cosine hyperbolic beta H effective. Okay. So, del ln ZMF by del H effective, now that is the term that we have here, the last line that we are now calculating, and this is equal to n beta tan hyperbolic beta H effective. Okay. So, we get this magnetization now is equal to tan hyperbolic beta H effective. Okay. So, this is the expression that we have to now solve. So, expression for magnetization. And why it is important? It is important because if M is non-zero, we have a ferromagnetic phase, and if M is 0, then we have a the paramagnetic phase. And this H effective, do not miss that this is a combination of the actual H, that is externally applied field, and a ZJM. Okay. So, this H effective is a combination of that. But now, something interesting occurs here in this last expression, which is the expression for magnetization. You have to solve for the magnetization which is there inside the argument of the tan hyperbolic term. So, this cannot be solved unless you solve it either iteratively numerically, or you treat this as a transcendental equation and try to this is a transcendental equation, of course, and try to arrive at a graphical solution. And this is what we will do. Instead of doing it numerically, we will do a graphical solution, and let me sort of sketch out the graphical solution for for some particular values of fixed values of beta H, Z and J. Okay. So, there is a graphical solution is what we need to arrive at. Okay. And it is easy to see that there are two regimes which are important, two regimes. One regime is your beta Z J is less than equal to 1, it is less than equal to 1, which tells you that J over or rather KT over ZJ is greater than equal to 1, okay, I mean greater than equal to. So, which means the thermal fluctuations dominate over the J term or the ZJ term. Now, you have to understand that there are competing behavior, that is the thermal fluctuations will try to disorder the spins, which means that they would allow not to order, and J will try to order. So, there is a competition, and these two competitions are what we are looking at. So, one is beta Zj, which is less than 1, and we have just put this less than equal to because the equality actually gives you a critical behavior. And the second region is important, where you have a beta Zj to be greater than 1. Okay. And this is where it is the other limit, that is Kt by Zj is less than 1, which means that the thermal fluctuations are subdominant and the interaction between the spins are dominant. Okay. If you solve these for each one of them, then what we get is that we get a solution like this. There is only and you have, so let me show you what is this. So, we have this as the LHS and this as the RHS, and we are solving the both sides of this equation. Okay. That is and so there is the both sides of the equation, and you see that for the first case you have only a ordering or rather these two plots, they only meet at t equal to 0. So, which says that the ordering is only possible at t equal to 0. And for the other case, you see that the plots would look like this. Once again, I am not drawing it very well, but it is a tan hyperbolic curve, and you have so you have only solution at t equal to 0 and one solution at plus m 0. So, this is m basically, and this is that minus m 0 and also at 0. So, 3 solutions corresponding to the second case. So, this corresponds to this and this corresponds to this. So, 3 solutions at 0 m equal to 0 plus minus m 0, and this is at m equal to 0, that is the only solution. So, we get t equal to 0 is an idealized case. So, you see that there is no ordering possible, but very importantly we can see that. So, this is actually, I forgot to mention this, please take a note of this, that we are talking about now h equal to 0 and explore whether the model in any dimension has spontaneous magnetization. So, that is the question that we ask and try to answer. Okay. All right. So, we put h equal to 0 and h equal to 0, it gives you these two limits. In one limit you have a solution only at this equal to 0, there is only one crossing at t equal to 0, and then there are three crossings rather. One is that ideal point, I mean this M curve. So, this is your LHS and this is your RHS. Okay. And you can see this actually more cleanly if you take the derivative. So, if you take the derivative of this, so ddm of tan hyperbolic beta j z m and look at this at m equal to 0, and then you will see that this is greater than 1, or this is, or there is just one solution otherwise. Okay. So, we take the derivative of this term and evaluate it at m equal to 0, and why we do that is that we basically look at this m equal to tan hyperbolic beta z j m, and then take a ddm of that and evaluate it at m equal to 0, this derivative, and this derivative is greater than 1. For beta j z, which is basically region 2, beta z j is greater than 1, and it has just one solution for the other region. Okay. So, nevertheless, what emerges finally is that there is a solution at h equal to 0. And clearly that is a wrong result in 1D. Okay. And of course, because there is this the ordering temperature in this particular case is nothing but is the KTC is equal to Zj, that is what we are. So, it is beta Zj when m is non-zero. So, your Tc becomes equal to Zj over k, and in 1D this Tc becomes equal to 2j over k. In 2D it becomes equal to 4j over k, which is wrong. 3D it becomes equal to 6j over k. So, this is completely wrong, qualitatively correct, but it is wrong, the numerical values are wrong. This is like 2.27 from Onsager solution, or 269 or something j by k, and this again is like 4 j by kb approximately. Okay. So, you see that it is getting better and better as you go in larger and larger dimensions. Okay. All right. So, this is a contrasting result that we get in mean field theory, and it is actually an inherent thing in mean field theory. This transition temperature does not exist in 1D. Any infinitesimal temperature would destroy ordering in 1D. That is the result that we got from the transfer matrix, and we should also should have also gotten this, but then this becomes infinitely wrong because the thermal fluctuations dominate. So, let me just one last thing that we do here is talk about the magnetization. And the magnetization can be obtained at least for T. So, we know that the magnetization is 0 for T greater than equal to T c. So, the magnetization vanishes, it does not order whether you have H or you do not have H. So, T c is given by, as we say, that T c is Z j over k, the Boltzmann constant. Okay. So, that we look for this solution that we have already gotten, m equal to tan hyperbolic beta Z j m, and we look at the 0 field solution again, 0 field solution, and which means that H equal to 0, and the 0 field solution gives that m is equal to now the tan hyperbolic x for small x can be expanded as x minus x cube by 3, x cube by 3 plus of the order of x to the power 5. So, these are all the odd terms that remain, and this is equal to if you do that expansion of this magnetization term, then it is beta Z j m minus 1/3 beta Z j m cube, and so on. And so, now what we do is that we do an expansion of this really at t equal to T c minus. So, we approach T c from the ordered side of the transition, which means where it was ordered we approach it from there, and then we have these m to be equal to T c over T into m minus 1/3 T c over T whole cube and m cube for T tending to T c from below. Okay. So, we sort of expand m, this is of course for small m. So, expand the self consistency condition. I will tell you what the self consistency condition is. The self consistency, because we had to solve a transcendental equation there. So, that is the self consistency condition. So, this is the self consistency condition. All right. So, we are fairly done, accepting that we can sort of take everything on one side, and this is of course for small m. This is because you expand it about m equal to 0, where the as t comes to T c either from below T c to towards T c or above T c to towards T c, the magnetization remains small. So, we just simply do a bit of simplification of that. So, it is a T c over T minus 1 minus 1/3 T c over T whole cube m square equal to 0, and this is the equation that we get, and then if you solve this equation it becomes plus minus root over we have a 3 T by T c whole square and Tc minus T over Tc, and this is how the magnetization behaves. And you see, as you put T equal to Tc, then of course it goes to 0, okay. But very close to Tc, the behavior of magnetization with temperature is given by this formula. So, it is m of T at T tending to Tc minus, okay. So, this is the formula for that, and then one can do further sort of analysis of that. In either case, what happens is that we get a scenario for m to be like this, okay. So, this is plus 1 and minus 1, this is m is being plotted as a function of T. So, this is Tc. So, we are really interested in knowing that what is the behavior here. So, this is the behavior here. I mean, we have shown it, let me draw it, that we are showing the behavior here when T is approaching Tc from below, okay, or it can also be in the other direction, that is fine. Okay. So, the physical interpretation is that above the transition temperature, the thermal fluctuations are so strong in 1D that they completely destroy any magnetic ordering of the system, and then we do not get any sort of magnetically ordered or a ferromagnetic phase. But however, getting magnetization below Tc in one dimension without magnetic field is a wrong result, which is what we have said. So, let me write this, that mean field theory is qualitatively correct in higher dimensions but gives wrong result in 1D. Okay. So, this is some sort of discussions of the magnetic phase transitions in the interacting systems, and it is important to understand that the interacting systems are actually very important, and they form the basis of real or rather when you need to deal with real systems, it is quite important to take into account interactions, and we are giving only very simple examples where we are doing statistical physics and arriving at solutions, arriving at implications, arriving at results which are of importance to us. One of the last things that we should do with this Ising model is the renormalization group, and we will do it quite quickly, but the implications are very important, and this is also called as the the poor man's RG, and this was invented by Kenneth Wilson in 1982, or rather it was written down earlier, and he got a Nobel Prize in 1982 for this discovery. In fact, one of the very few discoveries where owing to a completely theoretical work one has gotten a Nobel Prize. Okay, so this is one of the examples of that. And of course, we applied to 1D Ising model and show that the result that we have intuitively got or we have gotten through the transfer matrix approach is correct and the mean field solution is wrong, but the whole idea is not to re-emphasize the same result obtained again and again, but we are showing you different methods of dealing with interacting systems. Okay. Now, why is this renormalization group? So, what we do is that we take a 1D Ising chain and throw out certain degrees of freedom and cast the same system. So, suppose we throw out certain spins, we have n spins and we throw out certain number of spins and cast the same Hamiltonian or the same system in as it was as the original one, but now with renormalized coupling constant or renormalized J. Now, if we keep doing that and we arrive at a stage that this coupling constant is not evolving, that is, it's remaining same, that is, the spins are experiencing same exchange interaction even as you throw out more spins, or if you include more spins at that particular situation, then the system starts looking identical at all length scales. This has been sort of cursorily talked about earlier, that this really talks about a phase transition, because in a paramagnet, if you look at a certain number of spins, maybe 5 of them could be up and 3 could be down, and in some other region there could be 1 up and 4 down and so on, or 6 down. But for a ferromagnet, if you look at 5 spins or 50 spins or 5,000 spins or 50,000 spins, they all look to be ordered along the same direction. Okay? So, at the phase transition, there is a scale invariance that occurs, and this scale invariance is captured in our renormalization group analysis through the flow of the coupling constant. The flow stops, the coupling constant does not evolve. So, if you throw out more spins, the system becomes more sparse, but however this your coupling constant, which is J, it does not change anymore if you throw out more spins. It will become clear as I write this down. So, let me write down the partition function once again for this n spins, and we just write as a k, and k is simply equal to j over k. Well, kt, yes, this capital K is j over kt. Okay, we just write in a slightly shorter notation. So, it's S1, S2, all of them to Sn have values plus and minus 1, and we have this, we started with a full where each site is occupied by a spin which has got plus minus 1 value. So, S1, S2, S2, S3 and so on, and well, I mean Sn, S1, etc. Okay. So, the idea of this renormalization group, or which is in short called as RG, is to remove degrees of freedom and assess the system whether it retains the identical feature, or what happens to the renormalized system in terms of the coupling constant between the spins, which in this case we denote by K. So, for that we write down this partition function once again in terms of this S1, S2, etc. We what to write, and write it pairwise. So, it is an exponential k S1 S2 plus a S2 S3. Okay. So, we take pairwise and then take a exponential and S3 S4 k, S3 S4 plus S4 S5 and so on, and do it just pairwise, keep doing it. Okay. So, now we can do sum over these spins which have values plus minus 1. Now, sum over only even numbered spins, that is S2, S4, S6, that is you perform the sum S2 equal to plus 1 and minus 1, S4 equal to plus 1 and minus 1, and sort of let them leave the partition function by explicitly summing over them. Now, these variables are no longer would be there in that partition function. So, what we sort of look at is that let us look at number them as 1, 2, 3, 4, 5, 6. We will be left with 1, 3, 5 in the next iteration. So, it is 1, 3 and 5. So, this have a coupling constant k, this have a coupling constant k prime if you write the same form as earlier, and we want to see that how this k is flowing towards k prime, whether we actually achieve that the k prime is no longer evolving if we throw more degrees of freedom out of the system. And this is in that case the system starts looking identical at all length scale. Length scales means these difference between the spins are, they denote the length scales, and your k and k prime are dependent on that. It's very easy to see that k prime is smaller than k. Okay. So, we go from coupling constant from a larger one to a smaller one as we do that. On the contrary, if we start we start with a sparse system, that is an empty system, almost empty system, and then start filling up the spins, we would go from a lower coupling constant to a larger coupling constant, but they essentially they mean the same thing. So, we have then for this n by 2 spins, we then have we have S1, S3 etc., and which can be written as this exponential k S1 plus S3 plus exponential k minus k S1 plus S3, this for the S2 equal to plus 1 and minus 1. And for the next term where we do it for sort of S4, we get a S k S 3 plus S5 and a plus exponential minus k S3 plus S5 and so on. You do it on the even number of spins, and finally what will happen is that we would have to reach, or I mean if at all it is there, we have to reach a finite kc by doing further decimation of spins, that is you sum over more degrees of freedom, that you evolve your own algorithm, that which are the ones that you are going to throw out from the Hamiltonian and write down the new partition function for n by 4 spins and n by 6 spins, or any number of things that you want to throw out according to your algorithm, and see that whether you reach a k equal to kc, a critical coupling constant for which the iteration stops, that is kc kind of saturates and does not go to lower and lower values as you decimate more spins or integrate out more spins. Okay. So, we look for k and fk and a k prime, a new k or new coupling constant, such that these exponential k s plus s prime, that is any two spins, for example s and s prime where s1 and s3 in the first term, s3 and s5 in the second term, and a plus exponential minus k s plus s prime, that becomes some function of fk and exponential k prime s prime. You see, this is a quantity that we have to find out. It is a function of the coupling constant, but this has the form of the original Ising Hamiltonian, which is SISJ, original Hamiltonian. So, this we need to write the new problem, the decimated problem at the first stage, as the original problem in the second stage with a new coupling constant and some quantity fk which we need to figure out. So, this can be done as the z nk is equal to so S1, S2, S3, S5 etc. This is like a fk exponential k prime S1, S3 fk exponential k prime S3, S5. Let me just do one minor correction here. We have written this as n by 2 because we have summed over the spins, but let's at least at this stage let me write it still as n, because this has the information that S2 has been summed over and S4 has been summed over and so on. So, we still retain this, and then we have these further terms. Okay. So, this can be written as f of k, which does not include any of the s's, and this is like a n by 2, and then we have a z n by 2 k prime, and this is called as the recursion relation. Or it is also called as the Kadanoff transformation. Okay, so we have to determine f k and k prime. Okay, how do we do that? We take these combinations S equal to S prime equal to plus minus 1, that is 1. So, that gives us exponential 2k plus exponential minus 2k is equal to f of k and exponential k prime, and we take the other combination that S equal to minus S prime equal to plus minus 1. So, here they have the same sign 1, and in 2 we have opposite signs, which gives us 2 equal to f of k and e to the power k prime. Okay. So, there are two equations and two unknowns. Okay. Or we can also write this, say let's write this as equation 1. I will write it with a larger one, and these are 1 and 2, the normal fonts. Okay. So, these equations, of course 1 and 2 have two unknowns, and there are two equations, you can solve them. So, k prime becomes equal to half of log of cosine hyperbolic 2k. So, that is the k prime. Let us call this as equation 3, and I can also calculate f of k, which is 2 cosine hyperbolic 2k. This is equation 4. So, there were two unknowns, and we could calculate both of them, which relates the older coupling constant to a newer coupling constant, and also these quantity f k, which was introduced a link between the original system and the decimated system. Okay. So, we can write down a quantity which is, let us call it as a log of z n k is equal to some n g k, okay, where g k is like the free energy within a factor k t, okay, and a minus sign, of course. So, let us write a minus k t. Now, g k, the free energy, is of course extensive quantity, but since n is there, g k is an intensive quantity. That is, it does not change as you change the number of particles, volume, etc. So, let us write this down as equation 5, and hence we can go to this equation 1, this capital 1 that we have written. We get a log of z n k is equal to n by 2 log of f of k plus log of z n by 2 a k prime. Okay. So, this is let us call it as equation 6. So, this is the relationship between the partition function of these Zn and Zn by 2, and then if we comparing 5 and 6, Gk is equal to half log of f of k plus half g of k prime. Okay. and g of k prime is equal to twice g of k minus log of 2 cos hyperbolic 2k. Okay. And let us call this as equation 7. So, that is basically your g of k in terms of g of k prime in terms of g of k. So, these are called as this 3, 4 and 7 are called as RG equations, or they are called as flow equations, because the coupling constant flows. Okay. I mean, if the partition function is known for a particular k prime, then one can generate it using this recursion relation for a k for a different k, okay, after one has done this decimation. Okay. So, the inverse of this RG equation, that is this we have written k prime in terms of k, but if you want the inverse ones, then k is equal to half cosine hyperbolic e to the power 2 k prime and g of k. So, we have changed our variables from kfk to kgk. So, these are half g of k prime plus half log of 2 plus k prime by 2. Okay. And this can be called as equation 8 and 9. So, they are sort of similar things. You just have to remember that k is greater than k prime, because summing over degrees of freedom and you are throwing them out. If you do the reverse, that is, you are populating spins starting with a sparse system, then your notions of k and k prime would increase. And in fact, let us sort of start with an example in which you have a sparse system, so that we have k prime equal to 0.01, that is the coupling constant. So, you have a sparse system and we wish to populated system. Okay. And so, this here you have a Zn equal to 0.01 can be sort of approximated at Zn equal to 0, this 0 1. Okay. So, this is 0.01 and it is almost 0, and this is known because Zn, if you have completely free spins, each of them have 2 degrees of freedom, which are half and minus half, then Zn is nothing but 2 to the power n. So, we can calculate g of 0.01 is equal to just log of 2. Okay. So, we give an example here again for the 1D Ising model, and then if you start iterating equations 8 and 9, then we get, so this is the first stage, we get it as k equal to 0.100334, and g of k becomes 0.698147. So, this first step you can just check by putting this k prime to be equal to 0.01 and these two values that we have said, Zn is equal to 2 to the power n and g 0.01 equal to log 2. And then in the second step you get k is equal to 0.327447. These are numerical numbers that you need to work out and convince yourself that these are correct, and 0.745814, and please do it for 3-4 steps more and see that where it is going. You will see that actually the k that you get, the new k that you get, is flowing towards infinity. Okay. So, which means that this is actually called as a fixed point, and it is a trivial fixed point. And along with this another trivial fixed point called k equal to 0. Okay. So, what it means is that as you sum over the certain degrees of freedom, these coupling constant that increases more and more. We just saw just 2 steps here. It came from 0, almost 0.01 to 0.1 to 0.3 and so on. If you go on doing it, it will become larger and larger and will eventually flow to infinity. So, there is no Kc, which means the system does not order at any finite temperature. Okay. So, which means that the system flows monotonically from completely sort of ordered to so it basically it flows to a disordered state, and it says that if the fixed point does not stop, that is if fixed point keeps increasing, or rather the coupling constant keeps increasing, then that means that there is only ordering at t equal to 0, which is of course an ideal case. Okay. And so, we go into a state we start with a 1D Ising model, and we never reach an ordered state of the system at any finite temperature. Okay. So, in any case, if you do it for I just mention it, the results for 2D Ising model, and people have done this, and one gets that there is a ordering temperature, which is what even the mean field suggests or the transfer matrix suggests, where the expressions are a little more complicated. I am not deriving them, but just giving you the results, and this is like a 4k, and this is a gk prime is equal to 2gk. The flow equations are like that, log of 2 cosine hyperbolic 2k to the power half cosine hyperbolic 4k to the power half, and this, and so the fixed point is obtained at k equal to some kc, which is equal to 3 by 8 a log of a cosine hyperbolic of 4 kc, which is from the original problem. So, kc is equal to 0.50698, and that is nothing but j by ktc. Okay. So, j by ktc agrees well with the Onsager's result. So, j by ktc equal to 0.44069, and you also get a 0.50698, which is not too this is exact Onsager's result. Okay. So, which means that in 2D Ising model there will be an ordering, and there will be no ordering in 1D Ising model, as the flow goes all the way from 0 to infinity. There is no finite temperature at which there could be a ferromagnetic ordering in 1D Ising model. However, it does in 2D. The results that you see are quite nice, and RG is not possible in 3D, and the mean field as numerical calculations are only the guiding thing for 3D, whereas it gives you a 6 so j over ktc becomes equal to 6, or so tc becomes 6 j by k. Okay. So, we will stop the discussion on Ising model and wish to pursue other things in the interacting systems in the remaining weeks that we have for this course. Okay. Thank you very much.